We've talked about computing limits in terms of tables and graphs. Now we need to talk about computing limits analytically. To do so, we're going to need to come up with a couple of theorems. I won't be proving these theorems, at least not for the most part. The first theorem we're going to talk about is the limits of linear functions, that is, functions in the form mx plus b. We're going to say a, b, and m are all real numbers, and f of x is in linear form, mx plus b. If this is true, then the limit as x approaches a of f of x is simply equal to f of a. That is, we plug in a wherever we see x, or ma plus b. For instance, if I had the example f of x is equal to 2x minus 1/3, that is in fact a linear function, x is raised to just the first power, then the limit of x approaching 1 would simply be 2 times 1 minus 1/3, or the limit is equal to 5/3. You would be expected to simplify the expression 2 minus 1/3 into a single fraction. Let's look at one more example. If I had the function g of x equals 2, the limit of g of x as x approaches 1, well, it really doesn't matter what x is, because no matter what x is, g of x is always equal to 2. So this is simply equal to 2. This is a horizontal line, and even though there's no value of x, if we look at the function, the general function mx plus b, this is in fact a linear function with m equaling 0. 0 is in fact a real number, so it still meets our requirements in our theorem. I'm going to list now a bunch of other limit laws. For all of these limit laws, we're going to assume the following. We're going to assume that the limit as x approaches a of f of x and the limit as x approaches a of g of x do in fact exist. C is going to be a real number, and m and n are positive integers, that is non-zero and not negative. My first limit law is the sum limit law. It says if I have the limit as x approaches a of f of x plus g of x, it's equal to the separate limits, that is the limit as x approaches a of f of x plus the limit as x approaches a of g of x. The next limit law is the same thing, but we're dealing with subtraction. The difference limit law is exactly what you'd expect. Our third limit law is the constant multiple. If you have the limit of x approaches a of c times f of x, you can pull that c out, and it's simply c times the limit as x approaches a of f of x. Now the next limit law is one that makes me a little nervous, because although it works in this case, later on in calculus, you're not going to be able to do what you can with the limit laws. That is, the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Later on in the semester, when we get to derivatives and integrals, you will not be able to do this to products. So it's certainly a limit law, but keep in the back of your mind that you can't get too used to doing this, because in just a few weeks, you're not going to be able to count on being able to split up a product like this. Just like the difference law was similar to the sum law, the quotient law is similar to the product limit law. The power limit law says the limit of x approaching a of f of x to the nth power is the same thing as taking that separate limit, the limit as x approaches a of f of x, and raise that to the nth power. And finally, we deal with fractional powers. So the fractional power is just about the same as the power limit law. We just need to make sure that we don't have any negative square roots or fourth roots, etc. So this is true as long as if that denominator m is even, assuming that n over m is in lowest terms. If m is even, then f of x has to be positive for x near that value a. Otherwise, again, we'd have negative square roots, and we want to keep things real. Let's do some examples with these. Hopefully you have these written down, so I switch to the next page. I'm just going to refer to them both by name and number. For all these examples, we're going to assume the following. The limit as x approaches 13 of f of x is 3. The limit as x approaches 13 of g of x is 1. And the limit as x approaches 13 of h of x is negative 2. Here's my first example. So when we're doing these, we have to step by step state what limit law we're using. The first thing we need to do is split up the numerator and the denominator. We'll do that using the quotient limit law. You have to do these step by step. I don't want to see you listing multiple limit laws for a single step. The next thing I'm going to do is, with my numerator, I'm going to use the sum limit law. The last step will be to use the constant multiple limit law. And now we simply plug in the numbers to get our final answer. If you just wrote down 16 as an answer, you would get absolutely no credit. The point of this is to show that you can step by step use the limit laws to come up with the correct answer. Let's do another example. Here's our next example. The first thing I'm going to do is use the sum limit law. I'm going to take care of my first term, and I'm going to use the product rule for that. And my last step will be to use the power limit law. Now I'll just plug in my known numbers, and I get that the limit is equal to -5. And one final set of limit laws. That's the limits of polynomial and rational functions. The limit of polynomial p as x approaches a is simply p of a. To be honest, we didn't really have to come up with our separate linear function law because a linear function is in fact a polynomial. And if we have a rational function, that is a p of x divided by q of x, where p and q are both polynomials, then similarly to the polynomial function, the limit of x approaching a of p of x over q of x is simply p of a divided by q of a, as long as q of a does not equal 0. The question is, what is a polynomial and what is a rational function? Well, I'm going to talk about our rational function first. The word rational has the word ratio in it. A ratio is just p over q. It's two numbers, one over the other. The question is, what is a polynomial and what is not a polynomial? So this is an example of a polynomial. We have our variable x raised to integer powers. Well, actually not integer powers. They're all positive. Because if I had this, that is not a polynomial function because we have a negative exponent. Because that's the same thing as this, and that is not a polynomial. Similarly, square root of x, which is the same thing as x to the 1/2 power, those are also not polynomial. But these limit laws work as long as we have a polynomial and then a rational function with a polynomial in the numerator and a polynomial in the denominator. If I had an example like this, and I was told I can use the limit of polynomial and rational function laws, then I could simply use both of those to come up with the following answer. Now, keep in mind, there are times that I will ask to do problems without using these two limit laws. So be sure to pay attention to what the question's asking. If you have to use the sum, difference, constant multiple, etc. down to fractional power laws, be sure to use those. If you're told you can use the limit of polynomial and rational functions law, then you're allowed to use those. I'm going to go over one other type of situation where I'm talking about one-sided limits. The one-sided limits have the exact same rules as the limit laws, that is, limits that are the same from the left and the right-hand side. The only difference is that fractional power. And the only thing we have to focus on is the side that we're approaching. If m is even, again, f has to be positive or equal to 0 near a from the side we're interested in. So let's do an example of that. So here's our example. So let's start with number 1. That is finding the limit of f of x as x approaches 1 from the left-hand side. That's going to be this first part here, the x plus 4. By limits of linear functions, this is going to simply be equal to 5. When I'm approaching x from the right-hand side, the part of my function of f of x is the square root of x minus 1. Notice I've rewritten this as a fractional exponent. Since none of my limit laws had anything to do with square root signs, but I do have a fractional power rule, I'm going to go ahead and write it in this form. So, because near a from the right-hand side, if I'm approaching 1 from the right-hand side, from the positive side, that means x is approaching, say, 1.2, 1.1, 1.0001. X minus 1 is always going to be positive, so I can in fact use my fractional power rule. Now this is simply a linear function. It's simply 0 to the 1/2 power, or 0. My last question, what's the limit of f of x when x approaches 1? This does not exist because from the left we get a 5 and from the right we get a 0. Since the left and the right-handed limits don't match, the limit does not exist.